Very good morning and welcome to the lecture series session on EC402 nanoelectronics. My dear students, in the previous class we have discussed about the modulation doped heterostructures. First we learned heterostructures, what is heterostructures, how heterostructures are formed, and then we discussed about the modulation doped heterostructures. What are all the importance of modulation doped heterostructures and what is the band gap or band, what is the band energy on the conduction band when we have a modulation doped heterostructure formed by aluminum gallium arsenide heterostructure formation when two dissimilar semiconductor materials like aluminum gallium arsenide, which is almost n-type intrinsic or a lightly doped one, and gallium arsenide is a intrinsic type of semiconductor having very low impurities, or there is no doping or dopant added like that. So such heterostructures which makes a modulation doped one. So what are all the different behavior or the features which that particular device exhibit, that we have discussed. Now today we are going to discuss about the heterostructures which are strained at the interface. What is the strained heterostructure? So what has actually happened in the heterostructures when the surface of interface or interfacing surface of the structures are strained heterostructures, or they are strained, then we say that such heterostructures are strained heterostructures. What for we go for the straining of interface or strained interface for the heterostructures? Actually our aim is to get a very high mobility electron device, isn't it? High mobility electron device, so that if the mobility of the electron is very high in the 2D electron gas motion, then such device could be used for high frequency applications, or the device which can be operated at a very high frequency. So here the idea is to increase the mobility of the electrons. In what way the strained heterostructure helps us to get the mobility of electrons increased? So now let us discuss about this one now. The quality of an interface between two materials depends greatly on the relative size of the lattice constants. If the lattice constants are very similar, almost same as in the case of aluminum gallium arsenide heterojunctions, in that case of course the difference in the lattice constants are only 0.2%. The thermal expansion coefficient of these two materials are almost similar. Since the thermal expansion of the materials at the interface junction is almost similar, means that there is no stress developed at the interface. Those stresses are not introduced at the interface. Heterojunctions with the differences in lattice constants up to about 6% can be fabricated, or which are fabricated with almost 6% of difference in the lattice constants. For example, indium gallium arsenide. In this case, strong stresses appear at the interface. Indium gallium arsenide material on one side, indium gallium arsenide is there. On the other side, of course, very similar to our ordinary case, gallium arsenide is there. When we form a heterojunction with these two materials, high stresses are developed at the interface of the material, and this stress actually means to have some strain upon the interface. In this case, of course, very thin films of few nanolayers, usually called monolayers, can be grown on a given substrate. Heterojunction with this kind of devices or this kind of materials like thin films of monolayers, which can be grown on a given substrate. Say if the gallium arsenide substrate, we can grow heterojunctions on the substrate. Now strained layers are given here. So this is actually indium gallium arsenide and this is gallium arsenide. So here in the case of the first A, the layer is not deposited over the substrate. The layer is not separate. This is the lattice structure. This is the lattice structure for indium gallium arsenide, and this is for gallium arsenide. So independent lattice structure is shown here. Now the layer is subject to compressive stress. When these two dissimilar materials are joined together at the interface, the lattice structure formed by the material through the heterojunctions formed is like this. So this is the indium gallium arsenide and this is the gallium arsenide. So at the interface junction, of course, there are stresses developed. There will be compressive stress subject to the interface of the materials joined. Due to this compressive stress, what happens, this is the indium gallium arsenide side and this is the gallium arsenide side. Due to this compressive stress developed, there are dislocations formed at the interface. This is the dislocation. See the lattice constant. So this is a dislocation. So here there is dislocation. So likewise, there are dislocations developed at the interface. Now what happens? Suppose that a layer of lattice constant Al, the lattice constant is Al, is grown on a substrate of lattice constant As. The strain epsilon of the layer is defined as, what is the strain epsilon? The strain on the interface of the two dissimilar materials like indium arsenide or indium gallium arsenide or indium aluminum arsenide or gallium arsenide. For such materials, at the interface stress are developed and this strain on the interface of the two materials given by lattice constant Al for one material and As for the substrate material. Suppose the material substrate has a lattice constant of As and the material which is grown over the substrate is Al. Then strain is represented by the letter epsilon. Then epsilon is equal to, that is strain is equal to Al minus As divided by As. See, this is lattice constant. This is actually a parameter. That's a dimension of the material lattice structure. Okay, so Al minus As by As is the strain developed. Silicon germanium heterojunction, SiGe, usually we call SiGe. SiGe means silicon on one side, germanium on other side. So heterojunctions can be formed with this SiGe structure, which has got a large lattice constant difference between silicon and germanium. Around 4% lattice constant difference is there for silicon and germanium. It means that layers grow strained over the substrate. So in SiGe structure, definitely at the interface there will be strain developed and that strain will be always there at the interface. Our interface is subjected to the strain because SiGe structure has got a lattice difference of about 4%. In aluminum gallium arsenide, the lattice constant difference is only some 0.2%. See the difference. There are almost the expansion coefficient, everything are mostly same for both materials. Here the lattice constant difference is very high. So there is always expansion differently. So that is always compressive or stress developed at the interface. That may be a tensile or a compressive depending upon the case. So the layers are strained over the substrate. Since the energy gap of the silicon, for example, it is 1.12 electron volt. We know the energy gap of silicon is 1.12 electron volt. And that of germanium is about 0.66 electron volt. That is the energy gap. And this energy gap of germanium is fairly small, 0.66 only. The height of the barriers which appear at the interface should always be small. Since SiGe are strained, that is silicon germanium structures are strained, the degeneracy of the heavy and light hole bands is lifted. The degeneracy developed at the conduction band of the heavy and light hole bands are lifted. So SiGe heterostructures have found interesting applications in several fields such as high-frequency transistors and IR photodetectors. Due to this particular behavior, that is strained structures grown over the substrate, such type of devices can exhibit high mobility of the electrons, and that causes to make it as a, or to use this device as a high frequency transistor. Or this can be used as an IR photodetectors also, infrared photodetectors. So that is the main reason why we go for strained heterostructures or strained heterostructure devices. Okay. Now let us consider this band diagram. This is the energy band diagram for the Si-Ge structures. So here in this first case, of course, here the substrate is the Si-Ge. So substrate is, in the first case, substrate is silicon and strained active layer is Si-Ge. This is the strained active layer. See here, this is 0.11 electron delta Ec. Here it is 0.2 plus 2. This is minus 0.11 electron volt. This is plus 0.21 electron volt. So the interface between these structures are actually strained. So here the layer which is grown over the substrate is silicon. The layer grown is Si-Ge, where silicon has got almost 0.7 and germanium has got 0.3. Follow my point. So here in the Si-Ge structure, we can have a situation in which the silicon will be acting as the substrate and Si-Ge structure will be, the strained structure will be going over the silicon substrate. The same way we can have the Si-Ge structure as the substrate. Si-Ge as the substrate and silicon will be acting as the strained layer. So here the strained layer is silicon. See the difference? Here this conduction band we have already discussed about the conduction band gap for the two materials. Here it is, this energy gap is 0.29 electron volts. Here it is minus 0.07 electron volts for Si-Ge. So there is a huge difference. So in this two band diagrams of Si-Ge heterostructure, both are Si-Ge heterostructures only. In this particular heterostructure, Si-Ge heterostructure, here the active layer on this one is Si-Ge. That is, Si-Ge is grown over silicon. In the second case, B, here Si-Ge is the substrate and active layer is silicon. Follow my point. So this is the band diagram for Si-Ge heterostructures and how it happens, how the electron mobility and all those things happens, and how can we make use of it as a high frequency device. In figure A, the substrate is actually having grown the 001 direction. I have told you already that the momentum space, the substrate is grown on 001 direction, where Eg is 1.117 electron volt for silicon, and the strained active layer is Si-Ge, that is silicon 0.7, germanium 0.3, where Eg is equal to almost 0.78 electron volt. In this case, the conduction band offset is rather small in contrast to the valence band offset. That is the main reason. In the Si-Ge structure in which the silicon, which is used as the substrate, is grown in the momentum space 001 direction, and the strained active layer is the Si-Ge, where the conduction band offset is rather small. It is small compared to the valence band offset. And this particular condition allows the formation of a 2D whole gas. Actually, this particular situation, this particular condition of the substrate over which Si-Ge structure layers are grown helps us, or it actually forms a 2D whole gas not electron gas, it is Hall gas in the Si-Ge alloy, because here the active layer is the Si-Ge. So 2D Hall gas in the Si-Ge alloy is formed with electron mobility around 2 meters square per volt per Siemens. That is about half the value found for electrons in the MOSFET. Usually in the Si-Ge structure, the mobility of electron is found about half the value of MOSFET. So this is not a good option. Now let us consider the second option, that is in figure B. Here the situation is reversed. Here the strained layer is silicon and Si-Ge is acting as the substrate. Okay, or silicon layer is grown over the Si-Ge wafer or Si-Ge substrate. In this case, actually what happened? The discontinuity in the conduction band, actually the conduction band discontinuity, that is very important, and that is very large in the case of the second case, that is silicon as the strained layer. If the silicon is acting as the strained layer and Si-Ge as the substrate, then the conduction band discontinuity is fairly large and the electrons form a 2D gas. Here in this case, when silicon is used as the strained layer and strained active layer, which can produce or which can form a 2D electron gas produced with a free motion in the plane of interface. The silicon effective mass corresponding to this motion is the low transversal one, therefore yielding a very high mobility of around 20 meters square per volt per Siemens. That is several times higher than that of the MOSFET. See how the heterostructure, strained heterostructure formed by Si-Ge structure. That is strained here, the Si-Ge, actually silicon germanium is used as the substrate and silicon is actually grown over this particular Si-Ge structure as layers. So that at that interface, a 2D electron gas formation is possible because this structure, that is Si-Ge with silicon layers formed over the Si-Ge, will produce 2D electron gas at the interface, and this 2D electron gas attains a very high speed due to the discontinuity in the conduction band, and this discontinuity is fairly large, so that 2D gas formation is possible, and this 2D electron gas formed can have a free motion. But a 2D electron gas, it is not a gas. The 2D electron wave motion is called 2D electron gas. That is 2DG. Understand that? പലപ്പോഴും ബുക്കിലൊക്കെ നോക്കുമ്പോൾ 2DG, ഞാൻ തന്നെ ചില ഇതിലൊക്കെ എഴുതിയിട്ടുണ്ടാവും 2DG. It means that two-dimensional electron gas motion. So actually this gas motion, why we consider it as a gas motion? Because this material is actually quantized in one direction, isn't it? Since it has got the confined in one direction, confinement only two directions, these electrons can move, and such a quantization is done when the miniaturization is taking place. That is as a nano structure. This nanostructure, heterostructure, is acting as a nanostructure. When such a miniaturization is being done, all these phenomena takes place. That is why the electron gas. Why is it called electron gas? Because the phenomena which undergoes in the electron movement is a quantized one, so it attains a very high frequency, or it attains very high speed of motion on the plane of the interface. Follow my point? So that is why this particular electron will attain high mobility several times rather than the corresponding one as that of MOSFET. MOSFET high mobility attain ചെയ്യാൻ പറ്റും. That is why we go for Si-Ge structures, heterostructures sometimes. Si-Ge heterostructures അങ്ങനെയുള്ള high mobility device ഉണ്ടാക്കാൻ, high mobility electron device ഉണ്ടാക്കാൻ. Understand my point? Or can you got the idea? Okay. Now we can just have a comparison with the MOS structure. That is this heterostructures with MOS structure. The quantum well for the electrons produced at the aluminum gallium arsenide interface has a shape close to a triangle, as in the case of most. So here the quantum well formed has almost have the same shape as that of the triangle. That is, it is called a triangular quantum well. Therefore, if we call Z the direction perpendicular to the interface, if Z is the direction perpendicular to the interface of the heterojunction formed, the electron forming the 2D inversion layer are free to move along the xy plane. That we have several times we have told this one, isn't it? The Z direction we have the confinement. So the electrons are free to move on xy plane. So 2D inversion layers can be formed at the interface, isn't it? 2D inversion layer can be formed at the, if you fabricate a device with this kind of ideas of this kind of technology, this kind of theory, of course, 2D inversion layers can be formed at the interface. So, if we call a set the direction perpendicular to the interface, the electron forming the 2D inversion layer are free to move along the xy plane. But their energy for the motion along Z is quantized as in a potential well. So that you have to understand. Their motion is restricted on Z axis and that is quantized as in a potential well. The most important aspect of the heterojunction is that the charge carriers are located in a region, mainly in the gallium arsenide. In the case of aluminum gallium arsenide is the place, or it is actually the region where the charge carriers are located, and which are spatially separated from aluminum gallium arsenide semiconductor, which originates the free electron. So, in aluminum gallium arsenide heterostructure, the charge carriers are located on gallium arsenide side, where there is no dopant added, so impurity scattering is not there. So electron attains very high speed of motion. Understand that fact? Okay. Since they move within the gallium arsenide, which is free of dopant impurities, which is not having any dopant impurities, and that actually has to make the mobility of electron or carrier mobility very high, because there is no impurity scattering in the material, gallium arsenide material, due to the dopant-free nature of the material. This is one of the main factors which limit the carrier mobility, especially at low temperatures. So, impurity scattering is one of the main factors that we know. If the material in which the carrier concentration is there is having some impurity added to that particular material, that impurity scattering at one level, that is especially at low temperatures, the impurity scattering may happen. That way always adversely affect the carrier mobility. And that is not there in the case of aluminum gallium arsenide, due to all the conditions and things which we have stated here. So evidently, the electron mobility is so much higher than in the case of most structure. So it is due to this fact, the heterojunction devices, modulation of FET, are having very high speed as compared to most structure. FET based on this interface are MOSFET and HCMT. FET based means field effect transistor based on this particular interface, that is heterojunctions, are usually the MOSFET and HCMT. MOSFET and HCMT are the best examples for heterojunction transistors or heterojunction devices. Okay, thank you very much for patiently sharing this lecture session. We will discuss in the next class. We will discuss about the quantum wells, multiple quantum wells. Thank you.